Okay, welcome everyone. So today we'll be going over learning theory. This used to be taught in the main lectures in previous offerings. This year we're going to cover it as a Friday section. However, some of the concepts here we're going to be covering today are important in the sense that they kind of deepen your understanding of how machine learning kind of works under the covers. What are the assumptions that we are making, and why do things generalize, and so forth. So here's the rough agenda for today. So we're going to quickly start off with framing the learning problem, and we'll go deep into bias variance, a trade-off. We'll spend some time over there, and we'll look at some other ways how you can kind of decompose the error as approximation error and estimation error. We'll see what empirical risk minimization is, and then we'll spend some time on uniform convergence and VC dimensions. So let's jump right in. Right. So the assumptions under which we're going to be operating for this lecture, and in fact for most of the algorithms that we'll be covering in this course, is that there are two main assumptions. One is that there exists a data distribution D from which X, Y pairs are sampled. So this makes sense in the supervised learning setting, where we are expected to learn a mapping from X to Y. But the assumption also actually holds more generally, even in the unsupervised setting case. The main assumption is that there is a data generating distribution, and the examples that we have in our training set and the ones we will be encountering when we test it are all coming from the same distribution. Right? That's like the core assumption. Without this, coming up with any theory is going to be much harder. So the assumption here is that there is some kind of a data generating process, and we have a few samples from that data generating process that becomes our training set, and that's a finite number. You can get an infinite number of samples from this data generating process, and the examples that we're going to encounter at test time are also samples from the same process. Right? That's the assumption. And there is a second assumption, which is that all these samples are sampled independently. Right? With these two assumptions, we can imagine the process of learning to look something like this. So we have a set of XY pairs, which we call as S. These are just X1, Y1, XM, YM. So we have M samples sampled from the data generating process, and we feed this into a learning algorithm, and the output of the learning algorithm is what we call as a hypothesis. So hypothesis is a function which accepts an input, a new input X, and makes a prediction about Y for that X. So this hypothesis is sometimes also in the form of a theta hat. So if we restrict ourselves to a class of hypotheses, for example, all possible logistic regression models of dimension n, for example, then it's obtaining those parameters is equivalent to obtaining the hypothesis function itself. So a key thing to note here is that this S is a random variable. Right? This is a random variable. This is a deterministic function. And what happens when you feed a random variable through a deterministic function? You get a random variable, exactly. So, so the hypothesis that we get is also a random variable. Right? So all random variables have a distribution associated with them. The distribution associated with the data is the distribution of capital D. This is just a fixed deterministic function. And there is a distribution associated with the parameters that we obtain. That has a certain distribution as well. In a more statistical setting, we call this an estimator. So if you take some advanced statistics courses, you will call what you will come across as an estimator. Here we call it a learning algorithm, right? And the distribution of theta is also called the sampling distribution. And the what's implied in this process is that there exists some theta star or an H star, however you want to view it, which is in a sense a true parameter, the true parameter that we wish to be the output of the learning algorithm. But of course, we never know. We never know what theta star is, and when what we get out of the learning algorithm is going to be just a sample from a random variable. Now, a thing to note is that the theta star or H star is not random. It's just an unknown constant. When we say it's not random, it means there is no probability distribution associated with it. It's just a constant which we don't know. That's the assumption under which we operate. Right? Now, let's see what are some properties about this theta hat. So all the entities that we estimate are generally decorated with a hat on top, which indicates that it's something that we estimated, and anything with a star is like the true or the right answer, which we don't have access to generally. So, any questions with this so far? Yeah. Yeah. So this could be in case of like linear or logistic regression or linear regression, generally happens to be a vector. It could be a scalar. It could be a matrix. It could be anything, right? It's just an entity that we estimate. And sometimes H star can also be so generic that it need not even be parameterizable. It's just some function that you estimate, right? So yeah, so it could be a vector or a scalar or a matrix. It could be anything. Right? So let's see what happens when we. So in the lecture we saw this diagram for when we were talking about bias variance. So in case of regression, try to fit it through. And we saw that this was one fit. This was just I think it's a different color. It's just a straight line, and right. We saw this as the concepts of underfitting. This is overfit, and this is like just right. Right. So the concept of underfitting and overfitting are kind of closely related to bias and variance. So this is how you would view it from the data. So this is from the data view, right? Because this is X, this is Y, this is your data. And if you look at, look at it from a data point of view, these are the kind of different algorithms that you might get, right? However, to get a more formal sense, formal view into what's bias and variance, it's more useful to see it from the parameter view. So let's imagine we have 4 different learning algorithms, right? I'm just going to plot 4 different. And here, this is the parameter space. Let's say theta 1, theta 2. Let's imagine, we have just 2 parameters. It's easy to visualize, theta 1 and theta 2. Right? And this corresponds to algorithm A, algorithm B, C, and D. Right? There is a true theta star. Which is unknown. Right? Now, let's imagine we run through this process of sampling m examples, running it through the algorithm, obtain a theta hat, right? And then we start with a new sample from D, run it through the algorithm, we get a different theta hat, right? And the theta hat is going to be different for different learning algorithms. So let's imagine first we sample some data, that's our training set, run it through algorithm A, and let's say this is the parameter we got. And then we run it through algorithm B, and let's say this is the parameter we got. And through C, maybe here, and through D, over here. And we're going to repeat this, second one. Maybe here, here, and so on. And you repeat this process over and over and over. The key is that the number of samples per input is m, that is fixed, right? But we're going to repeat this process over and over, and for every time we repeat it, we get a different point over here. Right? So each point, each dot corresponds to a sample of size m. Right? The number of points is basically the number of times we repeated the experiment. Right? And what we see is that these dots are basically samples from the sampling distribution. Right? Now, the concept of bias and variance is kind of visible over here. So if we were to classify this, we would call this as bias and variance. Right? So these two are algorithms that have low bias. These two have high variance. These two have low bias, high bias, low variance, high variance. So what does this mean? So bias is basically checking is the sampling distribution kind of centered around the true parameter, the true unknown parameter? Is it centered around the true parameter, right? And variance is measuring basically how dispersed the sampling distribution is, right? So formally speaking, this is bias and variance, and it becomes pretty clear when we see it in the parameter view instead of in the data view. And essentially, bias and variance are basically just properties of the first and second moments of your sampling distribution. So you're asking the first moment, that's the mean, is it centered around the true parameter? And the second moment, that variance, that's literally variance of the bias variance trade-off. Yeah.
In the data view, the way that we're getting like these under and overfit is we're changing the dimension of the polynomial that we're fitting. So we're changing like the number of thetas.
Yeah.
But then in the parameter view, we always just have 2 thetas.
So this is a diagram where I'm using only 2 thetas just to fit, draw it on a whiteboard. So you would imagine something that has high variance, for example, this one, to probably be of a much higher dimension, not just 2, but it would still be spread out. It would still have like high variance. There would be points in a higher dimensional space, but more spread out. Right, so the question was, in over here we actually had more number of thetas, but here with the higher variance plots we are having the same number of thetas. So yeah, so you could imagine this to be higher dimensional. And also different algorithms can have different bias and variance even though they have the same number of parameters. For example, if you had regularization, the variance would come down, for example. We'll go over that. A few observations that we want to make is that as we increase the size of the data every time we feed in, so if this were to be made bigger, if we take a bigger sample for every time we learn, the variance of theta hat would become small. So if we repeat the same thing but with larger number of examples, so this would be more, all of these would be more tightly concentrated, right? So the spread is a function of how many examples we have in each iteration. Right? So as m tends to infinity, right? The variance tends to 0. Right? If you were to collect an infinite number of samples, run it through the algorithm, you would get some particular theta hat. And if you were to repeat that with an infinite number of examples, you will always keep getting the same theta hat. Now, the rate at which the variance goes to 0 as you increase m is, you can think of it as what's also called like the statistical efficiency. It's basically a measure of how efficient your algorithm is in squeezing out information from a given amount of data. And if theta hat tends to theta star as m tends to infinity, you call such algorithms as consistent. Right? So consistent, and if the expected value of your theta hat is equal to theta star for all m, right? So no matter how big your sample size is, if you always end up with a sampling distribution that's centered around the true parameter, then your estimator is called an unbiased estimator. Yes? So efficiency is basically the rate at which the variance drops to 0 as m tends to 0. So for example, you may have one algorithm where the variance is a function of 1 over m square, another algorithm where the variance is a function of e to the minus m. You can have, the variance can drive down at different rates relative to m. So that's kind of captures what's efficiency here. Right? Yeah. Yeah, so theta hat approaches, this is a random variable here. So here's one thing to be clear about. Here, this is a number, a constant, and this is a constant. But here, this is a random variable, right? So what we are saying is that as m tends to infinity, theta hat, that is the distribution, converges towards being a constant, and that constant is going to be theta star, which means at smaller values of m, your algorithm might be centered elsewhere, but as you get more and more data, your sampling distribution variance reduces and also gets centered around the true theta star eventually. Right? So informally speaking, if your algorithm has high bias, it essentially means no matter how much data or evidence you provide it, it kind of always keeps away from theta star. Right? You cannot change its mind. No matter how much data you feed it, it's never going to center itself around theta star. That's like a high biased algorithm. It's biased away from the true parameter. And variance is, you can think of it as your algorithm that's kind of highly distracted by the noise in the data and kind of easily gets swayed away, far away, depending on the noise in your data. So these algorithms, you would call them as those having high variance because they can easily get swayed by noise in the data. And as we are seeing here, bias and variance are kind of independent of each other. You can have algorithms that have an independent amount of bias and variance in them. There is no correlation between bias and variance. And how do we kind of fight variance? So first, let's look at how we can address variance. Yes.
When you talk of bias and variance, are you talking in the limit of transcending to infinity?
So bias and variance are properties of the algorithm at a given size m, right? So these plots were from a fixed size m. And for that fixed size data, this algorithm has high bias, low variance. This algorithm has high variance and high bias, and so on. Yeah, you can think of it as you assume like a fixed data size, right? So fighting variance. Right? So one way to kind of address if you're in a high variance situation is to just increase the amount of data that you have. And that would naturally just reduce the variance in your algorithm. Yes?
How can you know a priori the variance if you don't know theta star?
That is true. So you don't know upfront whether you're in a high bias or high variance scenario. One way to kind of test that is by looking at your training performance versus test performance. We'll go over that. In fact, we're going to go into much more detail in the main lectures of how do you identify bias and variance. Here we're just going over the concepts of what are bias and what are variance. So one way to address variance is to just get more data, right? As you get more data, your sampling distributions kind of tend to get more concentrated. The other way is what's called as regularization. So when you add regularization like L2 regularization or L1 regularization, what we're effectively doing is, let's say we have an algorithm with high variance, maybe low bias, high variance, and you add regularization. Right? What you end up with is an algorithm that has maybe a small bias. You increase the bias by adding regularization, but low variance. So if what you care about is your predictive accuracy, you're probably better off trading off high variance to some bias and getting down, reducing your variance to a large extent. Yeah.
Why does adding regularization increase the bias?
Yeah, we are going to look into that next. So in order to kind of get a better understanding of this, let's imagine, so think of this as the space of hypotheses, space of, right? So let's assume there is a true, there exists this hypothesis, let's call it G, right? Which is like the best possible hypothesis you can think of. By best possible hypothesis, I mean, if you were to kind of take this hypothesis and take the expected value of the loss with respect to the data generating distribution across an infinite amount of data, you kind of have the lowest error with this. So this is kind of the best possible hypothesis. And then there is this class of hypotheses. Let's call this class as H. Right? So this, for example, can be the set of all logistic regression hypotheses, or the set of all SVMs. So this is a class of hypotheses. And what we end up with when we take a finite amount of data is some member over here, right? So let me call this H star, right? There is also some hypothesis in this class, let me call it kind of H star, which is the best in class hypothesis. So within the set of all logistic regression functions, there exists some model which would give you the lowest error if you were to test it on the full data distribution, right? The best possible hypothesis may not be inside your hypothesis class. It's just some hypothesis that's conceptually something outside the class, right? Now, G is the best possible hypothesis. H star is best in class. Best in class H. And H hat is the one you learned from finite data. Right? So we also introduced some new notation. So epsilon of H is, you will call this the risk or generalization error. Right? And it is defined to be equal to the expectation of xy sampled from D of indicator of h of x not equal to y. Right? So you sample examples from the data generating process, run it through the hypothesis, check whether it matches with your output, and if it matches, you get a 1. If it doesn't match, you get a 1. If it matches, you get a 0. So on average, this is, roughly speaking, the fraction of all examples on which you make a mistake. And here we are kind of thinking about this from a classification point of view to check if the class that your output matches the true class or not. But you can also extend this to the regression setting. But that's a little harder to analyze. But the generalization holds to the regression setting as well. But we'll stick to classification for now. And we have an epsilon hat S of H. And this is called the empirical risk. Right, this is the empirical risk or empirical error. And this over here is 1 over m equal 1 to m, indicator of h of xi not equal to yi. Right? The difference here is that here this is like an infinite process. You're sampling from D forever and calculating like the long-term average. Whereas this is you have a finite number that's given to you, and what's the fraction of examples on which you make an error. Right? All right. Before we go further, there was a question of how adding regularization reduces your variance. So what you can see, or actually let me get back to that in a bit. So E of G, and this is called the Bayes error. Right? So this essentially means if you take the best possible hypothesis, what's the fraction? What's the rate at which you make errors? And that can be non-zero, right? Even if you take the best possible hypothesis ever, and that can still make some mistakes. And this is also called irreducible error. For example, if your data generating process, spits out examples where for the same x you have different y's in two different examples, then no learning algorithm can do well in such cases. That's just one kind of irreducible error. There can be other kinds of irreducible errors as well. And epsilon of h star minus epsilon of g is called the approximation error. So this essentially means what is the price that we are paying for limiting ourselves to some class, right? So it's the error between it's the difference between the best possible error that you can get and the best possible error you can get from h star, right? So this is an attribute of the class. So what's the cost you're paying for restricting yourself to a class? And then you have epsilon of h at minus epsilon of h star, and this you call it the estimation error. The estimation error is given the data that we got, the m examples that we got, and we estimated, using our estimator some h at. What's the error due to estimation? And this is like approximation, right? So the error on G is the Bayes error. The gap between this error and the best in class is the approximation error, and the gap between the best in class and the hypothesis that you end up with is called the estimation error, right? And it's easy to see that h hat is actually equal to estimation error plus approximation error plus irreducible error. Right? It's pretty easy. If you just add them up, all these cancel out, and you're just left with epsilon of h hat. So it's kind of useful to think about your generalization error as different components. Some error which you just cannot reduce it no matter what hypothesis you pick, no matter how much of training data you have. There's no way you can get rid of the irreducible error. And then you make some decisions about that you're going to limit yourself to neural networks or logistic regression or whatever, and thereby you're kind of defining a class of all possible models, and that has a cost itself, and that's your approximation error. And then you are working with limited data, right? And this is generally due to data, right? And with the limited data that you have, and possibly due to some nuances of your algorithm, you also have an estimation error, right? we can further see that the estimation error can be broken down into the estimation variance and the estimation bias. Right? And you can also therefore write this as approximation error plus irreducible error. Right? And what we commonly call as bias and variance are, this we call it as variance, and this we call it as bias, and this is just irreducible. So sometimes you see the bias variance decomposition, and sometimes you see the estimation approximation error decomposition. They are somewhat related, they're not exactly the same. So the bias is basically why is, bias is basically trying to capture why is H at far from G, right? Why is it staying away from G? Why did our hypothesis stay away from the true hypothesis? And that could be because your class is kind of too small, or it could be due to other reasons such as we'll see, maybe regularization that kind of keeps you away from a certain hypotheses, right? And the variance is generally due to, it's almost always due to having small data. It could be due to other reasons as well. But these are like two different ways of decomposing your error. So now, if you have high bias, how do you fight high bias? Fight high bias. So how would you fight high bias? Any guesses? Mm-hmm. Yeah, exactly. So one way is to just make your H bigger. Right, make your H bigger, and also you can try different algorithms after making your H bigger. And what this generally means is what we saw there was regularization kind of reduces your variance by paying a small cost in bias, and over here so let's say your algorithm has some bias, right? So it has a high bias and some variance, right? And you make H bigger, your class bigger, right? And this generally results in something which reduces your bias but also increases your variance, right? So with this picture, you can also see what's the effect of how does variance come into picture. Now, just by having a bigger class, there is a higher probability that the hypothesis that you estimate can vary a lot, right? If you reduce the space of hypotheses, you may be increasing your bias because you may be moving away from G, but you're also effectively reducing your variance, right? So that's the one of the trade-offs that you observe, that any step a step that you take, for example, in reducing bias by making it bigger, also makes it possible for your H hat to land at much at a wider space and increases your variance. And if you take a step to reducing your variance by maybe making your class smaller, you may end up making it smaller by being away from G, and thereby increase your bias. So when you add regularization, the question somebody asked before of how does adding regularization decrease the variance? By adding regularization, you're effectively kind of shrinking the class of hypotheses that you have. You start penalizing those hypotheses whose theta is very large. And in a way, you're kind of shrinking the class of hypotheses that you have. So if you shrink the class of hypotheses, your variance is kind of reduced because there's much smaller wiggles room for your estimator to place your h hat. And if you shrink it by going away from G, you've also introduced bias. That's like the bias variance trade-off. Any questions on this so far? Yeah.
Is the space of hypotheses the output for one training case, or is like an average of several trainings?
Yeah, you probably want to think of each of these, you probably want to think of this as a generalized version of this, right? So here we have like fixed theta 1, theta 2, but because you could parameterize them into a few parameters, you can kind of plot it in a metric space, but that's like a more general, like a bag of hypotheses. And but in any case, in both those diagrams, a point here is one hypothesis, a point there is one hypothesis. Here it's parameterized, here it's not parameterized. Yes? The thing is, so the question is, what if we shrink it towards H star, right? The thing is, we don't know where H star is, right? If we knew it, we didn't even need to learn anything. We could just go straight there, right? So, yeah.
We're not sure that our bias in that way is definitely going up, right? We're not sure.
With regularization? So the question is, when we add regularization, are we sure that the bias is going up? No, we don't know. And this is a common scenario, what happens, right? When you add regularization, you reduce the variance for sure, but you're very likely going to introduce some bias in that process.
So bias is also likely to go down, right?
So if you add regularization, you're shrinking your hypothesis space in some way. So you're kind of moving away from true G. So you're kind of adding a little bit bias. You're very likely to add some bias in that process. Yeah, so it's, so I would encourage you to, kind of after this lecture to think about this a little more slowly. It takes a while to kind of internalize the concept of bias and variance, and it's not very intuitive, but thinking about it more definitely helps. All right, any other questions before we move on?
What is an example of a hypothesis?
So an example of a hypothesis class, right? So an example would be the set of all logistic regression models, right? And when you do gradient descent on your logistic regression class, you're kind of implicitly restricting yourself to set of all possible logistic regression models. That's kind of implicit.
I thought when I do a learning, I'm fixing the model, right? So I'm not fixing an H.
So the H is the output of the learning algorithm, right? So you feed an input to your algorithm, right? This is not the model. This is the learning algorithm. Like this is like gradient descent, for example, right? And the output of that is the parameters that you learned that converge to, right? So yeah, you probably don't want to think about this as the model that you learned, but this as the training process. And the output of the training process is a model that you learn. And that is a point in the class of hypotheses.
Also fix a learning model, but then I will have a bunch of possible H.
Yes, so you fix the class of learning models. You say, I'm only going to learn logistic regression models, right? For different samples of data that you feed it as your training set, you're going to learn a different theta hat.
And then they're within the class.
Yes, they have to be within the class of hypotheses. All right, so let's move on. So next we come across this concept called empirical risk minimization. ERM. So this is the empirical risk minimizer. Right. So the empirical risk minimizer is a learning algorithm. Right. It is one of those kind of boxes that we drew. It is, so in the box that we drew earlier as a learning algorithm, right? So the diagram that we drew earlier, based on which we reasoned everything so far, didn't actually tell you what actually happens inside. It could be doing gradient descent. It could just do something else. It couldn't be, some smart programmer who's written a whole bunch of if else and just returns a theta. It could be anything, right? And no matter what kind of algorithm was used, the bias variance theory still holds. Right? Now we are going to look at a very specific type of learning algorithms called the empirical risk minimizer. Right? So, and this was, you feed into your algorithm and you get an H star, H hat, let me call it ERM. Right? Now, H at ERM is equal to, so what is ERM, empirical risk minimization? It's what we've been doing so far in the course. Right? We try to find a minimizer in a class of hypotheses that minimizes the average training error. Right? So for example, this is trying to minimize the training error. From a classification perspective, this is kind of minimizing the or increasing the training accuracy, which is different from what actually logistic regression did, where there we were doing a maximum likelihood or minimizing the negative log likelihood. It can be shown that losses like the logistic loss can be well approximated by the ERM, and this theory should hold nonetheless. Right. So if we are limiting ourselves to that class of algorithms which work by minimizing the training loss, right, as opposed to something that, say, returns a constant all the time or does something else. If we limit ourselves to empirical risk minimizers, then we can come up with more theoretical results. For example, uniform convergence, which we're going to look at right now. Right. So we are limiting ourselves to empirical risk minimizers and starting off uniform convergence. Right. So there are two central questions that we are kind of interested in. So one question is, if we do empirical risk minimization, that is, if we just reduce the training loss, right, what does that say about the generalization error of that? So that is basically E hat of H versus epsilon of H. So consider some hypotheses, right? And that gives you some amount of training error, right? What does that say about its generalization error? Like that's one central question we want to consider. And the second one is, how does the generalization error of our learned hypothesis compare to the best possible generalization error in that class? Right? Note we are only talking about H star and not G. Yeah, so H star is the best in class. So these are two central questions that we want to explore. And for this, we're going to use two tools. Right? So one is called the union bound. Right? What's the union bound? If we have k different events, A2, Ek, then these need not be independent. Then the probability of A1 union A2 union Ak is less than equal to the sum of if this looks trivial, it is trivial. It's probably one of the axioms in your undergrad probability class. The probability of any one of these events happening is less than or equal to the sum of the probabilities of each of them happening. Right? And then we have a second tool. Right? So second, it is called the Hufting's inequality. We're only going to state the inequality here. There is a supplemental notes on the website that actually proves the Hufting inequality. You can go through that. But here we are only going to state the result. In fact, throughout this session, we're only going to state results. We're not going to prove anything. So let Z1, Z2, Zm be sampled from some Bernoulli distribution of parameter phi, and let's call phi hat to be the average of them, m of zi, and let there be a gamma greater than 0, which we call it as the margin. So the Hufting inequality basically says the probability that the absolute difference between the estimated phi parameter and the true phi parameter is greater than some margin can be bounded by 2 times the exponential of minus 2 gamma square m. Right? Not very obvious, but you can show this. What it's basically saying is there is some parameter between 0 and 1 of a Bernoulli distribution. The fact that it is between 0 and 1 means it's bounded, and that's a key requirement for the Hufting's inequality. And now we take samples from this Bernoulli distribution, and the estimator for this is basically, and these are just zeros or ones. Each of the zi is either a 0 or a 1. You sample a 0 or a 1 with probability phi, and the estimator is basically just the averages of your samples, right? And the absolute difference between the estimated value and the true value, the probability that this difference becomes greater than some margin gamma, is bounded by this expression. Right? So there are a lot of things happening here. So you probably want to slowly think through this. So this is a margin, right? And this is like basically like the deviation or the error, right? It's the absolute value of how far away your estimated value is from the true. And you would like it to be closer. So you probably want your phi hat and phi to be not more than, I don't know, 0.001, right? So in which case, if the absolute value between the estimated and a true parameter is greater than 0.001, if that's the margin that you're interested in, then this the Hufting's inequality proves that if you were to repeat this process over and over and over, the number of times phi hat is going to be farther than 0.001 from the true parameter is going to be less than this expression, which is a function of m, right? And that is, you can kind of believe it, because as m increases, this becomes smaller, which means the probability of your estimate deviating more than a certain margin only reduces as you increase m, right? So this is Hufting's inequality, and we're going to use this. Yeah, questions?
So H cap is the same as H star, just that like H star is in the limit of m being infinite.
Not so. So the question is H star the limit of H hat as m goes to infinity? It is H star in the limit as m goes to infinity if it is a consistent estimator. Right? So we went over the concept of consistency. Right? Given infinite data, will you eventually get to the right answer? And if your estimator is not consistent, then it need not be. So in general, H hat need not converge to H star as you get an infinite amount of data. Right? So now we want to use these tools, tool 1 and tool 2, to answer our the central questions. Any other questions? Yeah.
For Hufting's inequality, is that saying that the phi that we're trying to estimate has to be pulled from a Bernoulli in order for this to be true?
This is a more limited version of Hufting's inequality, and yes, if we limit ourselves to a Bernoulli variable which has some parameter phi, and you take samples from it, and you construct an estimator which is the average of the samples of the zeros and ones, then this inequality holds. This inequality is called the Hufting's inequality. Yes.
In general, are most learning algorithms not consistent?
So if you're in general, there is this class of algorithms called maximum likelihood algorithms, maximum likelihood estimators, and a pure maximum likelihood estimator is generally consistent. If you include regularization, then it need not be consistent. Though I'm not very sure about that. Yeah, sure.
Yeah, so basically, like, you think of like a neural net where you have something that's completely, like a loss function is not convex, and then if you're creating descent on the parameters of the neural net, you're not guaranteed to converge to H star. You can easily get stuck in some local optimum. So in that case, creating descent on a neural network is not always consistent. Does that make sense?
Yeah. So basically. For the mic, what he responded was, if you have an algorithm like a neural net, which is non-convex, you may actually not end up with the same result, even if you increase the number of. So though I would probably call the fact, I would probably think of the non-convexity to be part of an estimation bias. Because you could, in theory, always find the global minimum of a neural network. It's just that there's some bias in our estimator that we are using gradient descent and we cannot solve it. Okay, so now let's use these two tools, and for that we're going to start. Have a look at this diagram, right? So over here we have hypotheses. Over here we have error, and let's think of this. There's actually one curve which I'm trying to make it thick and probably make it look like multiple curves. This is just one curve, and this we will call it as. So this is the generalization risk, or the generalization error of every possible hypothesis in our class, right? So pick one hypothesis that's going to be somewhere on this axis, calculate the generalization error, not the empirical error, the generalization error, and that's the height of that curve, right? And we also have something like this. Right? So this dotted line now corresponds to some h of s of h. Now let's sample a set of m examples, right, and calculate the empirical error of all our hypotheses in our class and plot that as a curve. Right? Any questions on what these two are? Yeah. It need not be. It's I'm just. In fact, this is very likely not even a straight line. You're just thinking of all possible hypotheses. It need not be convex. This is just to get some ideas, get better intuitions on some of these ideas. Yes? So the black line, the thick black line, is the generalization error of all your hypotheses, right? And let's say you sample some data, right? Let's call it S. On that sample, you have training error for all possible hypotheses. Right? We haven't not learned anything, right? This is the generalization error, and this is the empirical error for the given S. Right? Now, in order to apply Houghton's inequality here, right? So let's consider some HI. Right? This is some hypothesis. We don't know. So we start with some random hypothesis, right? And so by starting with some hypothesis, like think of this as you start with some parameter, right? And so the height of this line up to the thick black curve is basically the generalization error of HI is the height to the thick black curve. So let me call this epsilon of HI, right? And the height to the dotted curve up till here, and this is epsilon hat of HI. I'm going to ignore the S for now, right? And this corresponds to like the sample that we obtained. Now, one thing you can check is that the expected value of where the expectation is with respect to the data you sampled. So what this means is that for one particular sample, this is the generalization error you got. take another set of M samples, that curve might look some other way, and the height to the dotted line would be there. So in general, on average, if you average across all possible training samples that you can get, the expected value of the height to the dotted line is going to be the height to the thick line, right? That's just a fact. Now here, if you apply Houghton's inequality, you basically get probability of absolute difference between the empirical error versus the generalization error to be greater than gamma is less than equal to 2 of minus 2 gamma square. And I mean, this is basically, Houghton inequality we have right here, except in place of phi and phi hat, we have the true generalization error and the empirical error. Any questions on this so far? Right. So what we are saying is essentially the gap between the generalization error and the empirical error, right? The gap being greater than some margin gamma is going to be bounded by this expression, right? So loosely speaking, what this means is, as we increase the size m, if our trainings, if we plot the set of all dotted lines for a larger m, they are going to be more concentrated around the black line. Does that make sense? So take a moment and think about it. This dotted line corresponds to S of some particular size m. We could take another sample of a fixed set of examples, and that might look, I don't know, something like this, right? And take another sample of size m, and that might look something like this. Now consider the set of all deviations from the black line to every possible dotted line along the vertical line of HI, right? Now, this gap is greater than some margin gamma with probability less than this term over here, right? So it essentially means that if you start plotting dotted lines with a bigger m, right, where the set of all those dotted lines correspond to a bigger m, they are going to be much more tightly concentrated around the true generalization of that H. Does that make sense? Right? You're basically applying Houghton inequality to this gap over here instead of some phi. That's basically what you're doing. Right? Now, that's good, but there's a problem here. The problem here is that we started with some hypotheses and then averaged across all possible data that you could sample. But in practice, this is useless, because in practice, we start with some data and run the empirical risk minimizer to find the lowest H for that particular data, right? And which means that H and the data that you have are not really independent, right? You chose the H to minimize the risk for the empirical risk for the particular data that you were given in the first place, right? So to fix this, what we want to do is basically extend this result that we got to account for all H, right? Now, if we want to get a bound on the gap between a probabilistic bound on the gap between the generalization error and the empirical error for all H, what's that bound going to look like, right? And this is basically called uniform convergence. This result is called uniform convergence because we are trying to see how the risk curve converges uniformly to the generalization risk curve, how the empirical risk curve uniformly converges to the generalization risk curve. And that's called uniform convergence, which you can apply to functions in general, but here we are applying to the risk curves across our hypotheses. And we can show, I'm going to just skip the math. So this we showed using Hufting's inequality, and you can apply the union bound for unioning across all H. Except we can, first we're going to limit ourselves to, all right, so let me start over. So we got this bound for a fixed H, right? But we are interested in getting the bound for any possible H, right? So that's our next step, right? And the way we're going to extend this pointwise result to across all of them is going to look different for two possible cases. One is a case of finite hypothesis class, and the other case is going to be the case for infinite hypothesis classes. So what does that look like? So let's first consider finite hypothesis classes. So first we are going to assume that the class of H has a finite number of hypotheses. The result by itself is not very useful, but it's going to be like a building block for the other cases. So let's assume that the number of hypotheses in this class is some number k, right? We can show that, I'm not going to go over the derivation, but I'm just going to write out the result. It's pretty intuitive. So basically what we do is we apply the union bound for all k hypotheses, and we end up just multiplying that by a factor of k, right? So what we get is the probability that there exists some hypotheses in H such that the empirical error minus generalization error is greater than gamma is less than equal to k times the probability of any one, which is equal to k times 2 xp of minus 2 gamma square m. And this, we flip it over, we negate it, and we get the probability that for all hypotheses in our class, the empirical risk minus generalization risk is less than gamma is going to be greater than equal to 1 minus 2k minus 2 gamma square m. Right? So with probability at least 1 minus this expression, which we can call this delta, with probability at least so much for all hypotheses, our margin is going to be less than some gamma. Right? This is just Hufting's inequality plus union bound, and just negate the two sides. You get this, and you can go over this slowly. Later from the notes. The notes goes over this in more detail. Right? Now, basically, now what we have is, now let's let delta equals 2k minus 2 gamma square m. So we basically now have a relation between delta, which is like the probability of error, by here, by error I mean that the empirical risk and the generalization risk are farther than some margin, and gamma is called the margin of error, and m is your sample size. Yeah, so what this basically tells is, if your algorithm is the empirical risk minimizer, it could have been any kind of algorithm, but if it is the kind that minimizes the training error, then you can get, by just changing the sample size, you can get a relation between the margin of error and the probability of error, and relate it to the sample size, right? So what we can do with this relation is basically fix any two and solve for the third, and that gives us some actionable results. For example, you can fix any two and solve for the third from this relationship, right? And what that could mean is, for example, so you can choose any two and solve for the third. I'm only going to go over one of those. So let's fix gamma and delta to be greater than 0, and we solve for m, and we get m to be greater than or equal to 1 over 2 gamma square log 2k over delta. So what this means is, with probability at least 1 minus delta, which means probably at least 99% or 99.9%, for example, with probability at least 1 minus delta, the margin of error between the empirical risk and the true generalization risk is going to be less than gamma, as long as your training size is bigger than this expression. Right? That's something actionable for us, right? Theory can be useful. So this is also called the sample complexity result. Right? And basically what this means is, as you increase m and you sample different sets of data sets, your dotted lines are going to get closer and closer to the thick line, which means minimizing on the dotted line will also get you closer to the generalization error. So this is basically telling you how minimizing on the empirical risk gets you closer to generalization. Right? Okay, so we started off with two questions relating the empirical risk to generalization risk. Now let's explore the second question. What about the generalization error of our minimizer with the best possible in class? So let's look at this diagram again. Let's say we started with this dotted curve, right? And the minimizer of that would be H star. Right? This is H star. Sorry, the diagram is a little, let me erase the previous one. Right? So this is H at, sorry. So this is H at. And this has a particular generalization error. Right? That is the point of, let's assume we got this data set. We ran the empirical risk minimizer and we obtained this hypothesis. And when we deploy this in the real world, its error is going to be so much. Right? Now, how does this compare to the performance of the minimizer of the best possible? So this is H star, best in class. Right? Now, we want to get a relation between this error level and this error level. We got one bound that relates this to this, and now we want something that relates this to this. Now, how do we do that? It's pretty straightforward. So generalization error of h hat, that's this dot over here, is less than equal to the empirical risk of h hat plus gamma. So we got a result using Houghton and union bound that the gap between the dotted line and the thick black line is always less than gamma, right? And it's the absolute value, so we can write it this way as well. And this, right? So basically, we started from the thick black line, dropped down to the dotted line, and this is going to be less than the empirical error of h star plus gamma. Why is that? Because empirical error, the empirical error of h hat by definition is less than or equal to the empirical error on any other hypotheses, including the best in class, because this is the training error, not the generalization error, right? So which means, and this is less than or equal to, so we dropped from the generalization to the test, and we said this test is, this training error is always going to be less than the empirical error of the best in class. You see that the best in class is higher for the empirical error. And this again is now, this gap is also bounded because we proved uniform convergence, that the gap between the dotted line and thick line is bounded by gamma for any h, right? And this is therefore h star plus 2 gamma, because we added the extra margin. So we wanted a relation between our hypothesis generalization error to the generalization error of the best in class hypotheses. So we dropped from the generalization error to the empirical error of our hypotheses, related that to the empirical error of the best in class, and again bounded by the gap between these two. So we got a gap between the generalization bound, the generalized error of our hypotheses to the best in class generalization. Any questions on this? Okay. So the result basically says with probability 1 minus delta, and for training size m, the generalization error of the hypothesis from the empirical risk minimizer is going to be within the best in class generalization error plus 2 times 1 over 2m plus log 2k over delta. So this was basically, so you can get this when you so in this expression, if you set this equal to delta and solve for gamma, you will get this. Any questions? I think we are already over time. So the case for infinite classes is an extension to this. Maybe I'll just write the result. So there is a concept called VC dimension, which is a pretty simple concept, but we won't be going over it today. VC dimension basically says what is the, so VC dimension is, you can think of it as trying to assign a size to an infinitely to an infinite size hypothesis class. For a fixed size hypothesis class, we had like k to be the size of the hypothesis class. So VC of some hypothesis class is going to be some number, right? Some number which kind of which is like the size of that hypothesis class. It's basically telling you how expressive it is, and on using the VC dimension, there are very nice geometrical meanings of VC dimension. You can get a bound, a similar bound, but now it's not for high. It's not for finite classes anymore. Some big O of right. So in place of this margin, we ended up with a different margin that is a function of the VC dimension. And the key takeaway from this is that the number of data examples, the sample complexity that you want is generally in order of the VC dimension to get good results. That's basically the main result from that. Right. From with that, I guess we'll break for the day and we'll take more questions.